morning, everyone, and welcome to another lesson on energy. Today's driving question: how is energy stored, used, and transferred? Starter: which would you buy and why? Pause the video, think about the two bulbs, ask a family member to look at the questions with you, and have a go. Which would you buy and why? Now take 5 minutes and attempt the questions. Welcome back. Now looking at the two bulbs, it's very obvious which one you should buy. But if you are not sure, let's show you why. Now looking at this bulb, we realize that it uses 800 watts of energy. Now watts, this is equal to 1 joule per second. Now, there's no need for you to worry about going into what the W means, because that's for another lesson. It lasts for 1,500 hours, and it costs only 50p. Now, going to buy a bulb, you see 50p compared to £2. You are more inclined to purchase the one for 50p, innit? Well, looking at this one, let's see if it makes sense. Now, it produces the same light as an 80-watt bulb, but only use 20 watts. So it uses 20 watts of the 80, which means that it uses 60 watts less compared to this bulb, even when producing the same amount of light energy. Now, this bulb lasts at least 12 hours, 12,000 hours. This one lasts only 1,500 hours. Now, let's say that we divide the 12,000 hours here by 1,005, we end up with 8 bulbs. All right, we end up with 8. Now, let's say for this one bulb, the duration will be using 8 bulbs for the same time period. Again, this bulb lasts for 12,000 hours. This one lasts only for 1,500 hours. Now, we divide 12,000 by 1,005, we end up with 8. So for every one of this bulb, we'll use 8 of these bulbs. Now, if you look at the cost, one of these bulb cost £2. This one costs 50p. However, we're going to take 8 of these bulbs to last 12 hours. If we multiply the 50p by the £8, by the 8 bulbs, we would end up with a total of £4. So this bulb would make more sense for you to purchase because one, it's cheaper, and this one bulb does the same amount of work as 8 of these bulbs. So I hope that makes sense. Now, where does energy comes from? The sun, food, power stations. This young man doesn't seem to know either. This one knows. You remembered what Mr. Samuels said in the last lesson? Do you remember what I said in the last lesson? This is what I said. Almost all food energy comes originally from the sun. The chemical elements that make up the molecules of living things pass through food webs and are combined and recombined. At each link, some energy is stored, but much is lost along the way in a form of heat into the environment. So, yes, the sun is the source of all energy. But even though that's the answer, yes, the sun, They are all stored differently and used differently. I know the sun is the main source of energy, but where does this energy, or where is this energy stored? Hmm. Factories. Well, the energies produced in a factory can be stored here, but they have to be harnessed or gained from different sources. Now, a power station is an industrial facility that generates electricity from primary energy, such as solar from the sun, thermal, and also chemical. Most power plants use one or more generators that converts mechanical energy into electrical energy in order for use in the wider society. Nature. Now, to say nature, nature is a very vague term to use. Now, if we look at different areas in nature, then we can identify different energy stores. Yes, the plants that you're seeing in the picture will store energy in the form of glucose, which is chemical energy. However, the water that you're seeing, let's say that it flows over a dam, a reservoir, that's another source of energy. If we're looking at the air, even though we can't see air, but we know it is still there, we can get energy from the air itself. Now, other man-made objects in nature can also store energy, such as batteries, and even some nuclear energy, which comes from the sunlight. Now, that's just a few, or those are just a few of the areas in nature that energy is produced. Do you want to know where energy is stored? Yep, here are the ones I remembered. Now, in our last lesson, we looked at a few of the energy stores, but we did not list all of them. So here goes. There are a few energy stores such as chemical, kinetic, gravitational, thermal, and elastic. However, that's just listing one, two, three, four, five energy stores, and we have a total of eight. Good try, Rob, but you are missing a few. Here are eight energy stores. Chemical, which we mentioned in the last video, in our last lesson, which looks at energy stored in the bonds of chemical substances. Gravitational potential energy, energy possessed by a body or object above the ground. Kinetic energy, the energy a body has because of its movement. Thermal, the energy or temperature of the particles within a substance. That means that a temperature change. Elastic energy, which is formed by the deformation of an object. Vibration, we know that as objects move, they give off energy. Nuclear, nuclear generates energy from nuclear reactions, such as nuclear fusion of hydrogen and helium, for example, the sun. And finally, electromagnetic. And this is energy that is emitted or reflected from objects through electrical or magnetic waves traveling through space. For example, X rays and UV. Now, let's have a look at some of these energy stores and where they can be found. Now, energy resource. Now, fossil fuels. Fossil fuels are found in soil. In most cases, these oil rigs extract the chemical or oil from which energy is produced. Now, once they dig these fossils up, this energy is stored as chemical energy. Now, is it renewable? It's non-renewable. So after a while, once all of this oil or chemical is removed, it will not be replenished. This form of energy is used in transport, heating, electricity generation. Power output is very high. Environmental impacts, it releases CO2, which causes global warming. Nuclear fuels. Nuclear. Is it renewable or non-renewable? It's non-renewable. It is used in electricity generation. Power output is very high. But this one is very tricky because it produces radioactive waste, which needs to be disposed of safely. Biofuel, energy store, chemical. It is renewable. It is used in transport, heating, and electricity generation. Power output is medium. Impact on the environment, carbon is neutral, so low impact. Wind, particles moving, which means that the store is kinetic. We always have wind, which makes it renewable. And this is used to generate electricity from a windmill. Power output is very low. Takes up large areas that could be used for farming. Some people say windmills spoil the view. Hydroelectricity from water. Remember the dam? Yes. Gravitational potential. Is it renewable? Yes, it is. What is it used for? Electricity generation. Power output, medium. Impact. Local habitats are affected by the large areas that used are, my apologies, local habitats are affected by the large areas that need to be flooded to build dams. Geothermal, the digging up of the soil or the earth to get heat or steam. Internal thermal. Is it renewable? Yes. Uses electricity generation and heating. Power output is medium. Impact very low. Tides. Again, we go to the ocean, we see the tides, the waves coming in. It's kinetic, it is moving. Is it renewable? Yes, it is. What is it used for? Electricity generation. Output potentially very high but hard to harness. Impact. Tidal barrages can block sewage, which needs to go out to the sea. The sun, nuclear. Is it renewable? Yes, it is. It is used to generate electricity and for heating. Output dependent on the weather and only available during daylight. Impact on environment is very little. Last but not least, water waves. Again, waves, it's moving, which means that it is kinetic. Is it renewable? Yes, no, yes, it is. Uses to generate electricity. Power output is very low. Impact on the environment is also very low. Just remember that animals get and use and store energy differently. Let's see how much can you remember from year 7. Well, you're still in year 7, but those who are in year 8, let's see what you can remember. Looking at the human body, we know that we have body systems, right? Our body systems can be divided up into organ systems, such as the circulatory system, the nervous system, the respiratory system, digestive system, the skeletal system, and the muscular system. All these body systems can be divided down into organs, such as the brain, the heart, the pancreas, kidney, the bladder, the intestine, liver, lungs, etc. Now, these organs can be further divided down into tissues. All right. And we know that our tissues are made up of cells. Now, what happens in the cell? We know that we breathe, we take in oxygen. We also eat. We get glucose. We absorb glucose. Now these two goes into the cell. The cell is a site for respiration. Now what happens in the cell is that glucose and oxygen goes in, and carbon dioxide, water leave as the waste product, and energy is produced. Now the energy produced in our bodies is actually stored as chemical energy. Now, I will not be going any further into this because this runs into your next lesson. Now, for those who did not understand what I said, now this is a chemical reaction which uses glucose and oxygen to release energy. This is what we're talking about. It releases energy. The glucose reacts with oxygen and is oxidized. So as you can see, glucose and oxygen goes into the red blood cell. Carbon dioxide and water leave as the waste product, and energy is given off. But this energy is stored as chemical energy. What is the energy in respiration used for in an organism? It is used for movement, growth, building of new molecules, maintaining the body temperature, among other things. Tip: energy is not produced or made in respiration. It is energy that is released. So again, energy, remember the law of conservation, which we'll be looking at. So remember that the energy is not produced or made in respiration. The chemical reaction that takes place in aerobic respiration takes place in the mitochondria, which is an organelle found in animals and plant cells. Remember, plants respire as well. No, but always remember that the way how our body gains, stores, and use energy is different to the energy that is collected, converted, and stored in our factories. Now, this is a factory somewhere in the UK. Now, once the energy is produced, it is sent out to our lovely school, Folkestone Academy, also to our homes in Folkestone, and also to our bigger companies. So they produce energy that is sent out to our schools, our homes, and the workplace. But what happens once the energy goes? Blackouts. And again, in this picture, you can see different light sources, which means that energy is stored somewhere to produce the light. And we end up have to use a candle. Remember, in a candle, energy is stored as chemical, but it leaves in the form of heat and light. Blackouts are caused by a range of factors. Extreme weather is the main cause for blackouts in the UK. Strong winds take down trees that knock out transmission lines. Snow and rain leaves damage to substation and other infrastructure, not to mention making it very hard for engineers to fix. So the next time you have a blackout, just bear in mind the men and women out there who are trying to restore your energy supply. Now, this is something for you to remember: the law of conservation of energy. Remember, energy cannot be created or destroyed, but is transferred from one store to another. In all of the experiments, there was an energy store at the beginning and at the end. All right? The only thing that changes or changed was the amount of energy in the store. And let's show you why. We use a Sankey diagram to represent energy that is used and energy that is given off. In all things, energy that a system starts with will not be the same energy that it ends with, because some energy will be used usefully while some will be lost and be wasted. Now let's look at this. So let's say energy diagram can also be shown as Sankey diagrams. Now chemical energy produced is 10 joules. Now out of these 10 joules, guess what? Light, which is useful, which is what we need, uses a total of 8 joules. However, from the light, we get heat. So have you ever been in a room, you turn the light bulbs on, you get the light. The light is what you want. But the room starts to get hot for after a while, which means that heat is also given off, which is a waste product. Now the diagram at the bottom gives us a general depiction of what the slinky actually looks like. So this big section tells us the amount of useful energy, and this section tells us the amount of energy that was wasted. So 10 joules of energy went in, 2 joules were wasted, and 8 were actually useful. Even though energy can't be created or destroyed, it can be wasted. Missing energy. Can you spot the wasted energy? Take a look at the light bulb. What do you think, or how is it that energy is being wasted from a light bulb? Think about a power drill. How is it that energy is being wasted or lost? Can you have a go? Ask someone in your house to assist you with this one. Welcome back. Now, looking at the bulb, light bulb is very useful. Now, a light bulb will lose energy in the form of heat, thermal. But the useful bit that we need is the light. So even though the bulb is producing light energy, it is also producing waste in the form of heat or thermal energy. Looking at a power drill, what were the wastes that you came up with, and what was the one good thing that came from the drill? One of the things that are waste when using a drill is heat. Now, if you ever used a power drill before, you will know that one, the drill becomes hot after a while. So that's heat. Two, it is very noisy. Have you ever heard someone using a power drill? It's very noisy. And the only good thing that comes from it is the drilling itself, the motion of the drill turning, which creates the hole or forces the screw or nail into an object. That's very useful. Now, a washing machine. Now, that's why it is very important for you to tell your parents that it is not okay, well, if they have enough money to, waste, being that's what we're talking about, then they can wash 4, 5, 6, 7 times a week. However, it is very costly to be washing every minute. Now, let's look at this. 100 joules per second transferred as light and sound. Now, this energy, once you see light and sound, we know that this energy was wasted. Yes, it was wasted, light and sound. Now, from that, 100 joules as useful energy. So, being that we have two outputs, 100 joules were useful and 100 joules were wasted. How many joules of energy was actually added at the beginning? 200. So 200 joules supplied as electrical energy, and of that 200 joules, only 100 was useful. So we wasted 100 joules of energy, which we will eventually have to pay for. So it is wise to wash once a week. But again, if you want to wash one shirt at a time, it's going to cost you more. So think wisely and think about it. Now, last but not least, this is also another way of wasting electricity. Yes, it's not something that we like, but it does happen. An electric shock occurs when a person comes into contact with an electrical energy source. Electrical energy flows through a portion of the body, causing a shock. Now, not in all cases you'll die. It takes roughly 8 minutes after being exposed to electricity to cause death. Again, it causes death after 8 hours, 8 minutes, sorry, of being exposed to this energy. Now, for the last activity, please identify 3 energy stored in your house. Take a picture of them and upload it to the drive. Again, please identify 3 energy source in your house and take a picture of them and upload them. Until next time, keep safe.